the notes. This is just what we had up yesterday, so I'm just going to quickly run back through this again. Reiterate this. We're going to come back to this a little bit today. This limit definition that kind of started us down this path of working on limits. This was a special limit, right? This was slope between 2 points, a plus h and a. All right, and then h going to 0 made the 2 points become 1. Now we've noticed that we could have limits where x approaches 3 or x approaches 2. There's nothing magical about x approaches 0. In this limit, though, there is something very important about h approaches 0, right? Because that makes the 2 points become 1. So a definition of a limit will always have this thing approaching 0. Okay? Now, but the a could be different things. I don't want you to confuse those, and you'll see later on what I'm talking about. But like this could be finding f prime at 3. Well, the 3 would be in here, right, where the a is. This will always be 0 right here, right, in the definition of limit, because that's the 2 points becoming 1. Right? So if we're finding the slope at 3, slope at 4, that's this a value that's in here. Doesn't have anything to do with this. Okay? All right, and so that's kind of doing things out the long way. Then we learned those shortcuts, of course. We'll work a little bit more with those today. And we had this thing about limits. And, of course, we said the first thing you do with limits is substitution, kind of like on your one with the calculator today, although many of you probably didn't substitute. You went right to the table, which was okay. You have substitution. And if this was a no calculator part of our next quiz, you would try substitution. If it didn't work, if you got a number, you would just put that down. There's your answer. If you get 0 divided by 0, you say, well, I need to keep going. That's indeterminate. There might be a limit. And I would do these techniques. I would factor and cancel. I would get a common denominator and cancel. I would conjugate and cancel. The key being the canceling, because that'll get rid of that 0 over 0. And then you'll probably get a number. And then you'll be done. Or you might get like 6 over 0 or 2 over 0, which, of course, you might have got right in the beginning when you did your substitution. And then we just say the limit does not exist, if that happens. So anytime we're just doing a no calculator, just algebra stuff, the only time we'd get limit does not exist would be, when we get this number divided by 0. Now, if we're doing tables, okay, that's another story. And we'll talk about your worksheet here in a minute. I've got a table up here. Let's see, somewhere, right here. Okay, this is another thing I might do on the quiz, is just say, okay, here's a function f of x, and I'll just throw this table up here at you, and I would ask you, okay, what is the limit as x approaches 3 of f of x? And just ask you for that answer. And what would you say? You would say, if you were going to get it right, you would say 5.371, right? And this 27 here doesn't matter, right? This would be kind of the equivalent of this thing right here. The cars are meeting at 5.371. The 27 doesn't matter. What if that would have been a 13? Doesn't matter. If it would have been, I got to sneak this in here somewhere. Mr. Martin mentioned it the other day, so what the heck. What if this was a German short hair?
Doesn't matter.
It doesn't matter, right? I might even do that. I'll put a peanut in there or something. I don't know. It doesn't matter. As far as what your answer to the limit is, it doesn't matter what's in here. Undefined, whatever, the limit is this. And didn't that happen on one of them? Was it number 6, 7? Didn't you have a 1 in there? You had a 1 in that middle one, and all around it was 2.718, right? So on that one, the limit was 2.718. Okay? I think that was, number 7. So the limit would be 2.718, not the 1. Okay, that's actually a calculator error that is making that happen. This might not be a bad time to just do that one. What was number 7? You had the function in parentheses was 1 plus x. 1 plus x raised to the 1 divided by x, right? Now, if you think about that, if you plug a 0 in for x, think about what you're asking it to do. You're doing 1 divided by 0, which is undefined. And if you put a 0 in for x here, you have 1 raised to the undefined. That seems strange, right? Why did your calculator put a 1 there? Well, what's 1 raised to anything? 1 to the second, 1 to the third, 1 to the fourth? It's 1, right? 1 raised to anything is what? Well, that's not quite true. Not anything. We just saw 1 raised to undefined actually shouldn't be anything, right? I mean, you can't. How can you do that? Well, your calculator, this is a little bit of a dilemma in your calculator. So if we go to our table, and, all right, if we go to our table, and I'll go to my table settings. A lot of yours are already set from yesterday. Okay, we want to start our table at 0. If you need some help with this, come in and see me or see somebody else or watch the video from yesterday. And we did it 2 days ago also. If we set our table, all right, and we put 0 in the middle, sure enough, we can see that the values are approaching 2.718. Right here on our, the cars would be coming in right here at 2.718. Okay, there's a 1 there. Well, actually, your calculator doesn't know quite how to handle that. And it's putting a 1 there because it's going, wait, where 1 raised to something is going to be 1, and so it's putting a 1 there. That 1 really shouldn't be there. Okay. If I go on the home, let's go on the calculator screen a minute, and let's just try that. Let's do 1 raised to the 1 divided by 0. Look what it does. It gives you a 1, but look at the warning down here. That's a warning. It says, I just gave you an answer, but you might want to be suspicious of it. That's kind of what the calculator is saying. I gave you this answer, but maybe you don't want to trust it. It's saying 1 to the infinity or 1 to the undefined is being replaced by a 1. Okay? And so sometimes the calculator can't quite handle some of these things that are going on. All right? But that's okay. In this context, that's perfectly fine for us. We don't care. We're not looking at that. If that's a German shorthand, we don't even care. It's 2.718 is our limit. All right. So I'm jumping around here a little bit. Let me come back to what we were just, let's come back to this. So there could be some cases where, what are things approaching? And so calculator tables. And then, of course, the other thing we want to be able to do are graphs. And graphs would be like the ones where on your homework out of the book the other day where you had this big piecewise function with gaps and breaks and everything, and I asked you for limits there. Well, those are easy. You just look, do the cars meet? One-sided limits from the left and the right. Those are easy to do with tables, and those would be easy to do with graphs as well. On the algebra, not so much. On the algebra, we pretty much just work them out and get those possibilities. Okay, so those are limits. So we'll see a little more of those on Monday, maybe practice a few and that kind of thing. All right, and then we had the one today, number 21. We'll work through that in a minute with the chart stuff and all that. Yes, Sean. Yeah, good question. Were there any that did not exist on the worksheet? Let's go through this. Which ones? 4 and 6 and 10. Okay, so let's just pick one. Usually, help me out here. I'm sorry, I don't have the answer key here. I still can't find that darn thing. So I didn't get a chance to type all these in. Are they all because they go to infinity? Or wasn't there one that went negative half and positive half? That was 10. Okay, so how you tell is, well, let me just bring back, probably the easiest thing is bring back this table right here. If this would have been this, if this would have looked like that, then that would be a does not exist. Because from the left, they seem to be approaching negative 5.371, and on the right, they're approaching positive 5.371. So the graph would be doing this, right? So the cars aren't meeting. So that'd be a does not exist. Another very common one is the infinity thing. And the nice thing about doing them on your calculator is you got the graph right here next to it. So if you see the graph going up like this and coming down like this, and you look at these numbers and they're big numbers like infinity, well, then you know that that's what's going on. Like if I arrow up, the nice thing is when you arrow up on one of these cells, you get this little sticky here that shows the actual number. So you can tell if you're getting like a scientific notation one, right? Because sometimes you get a number like this and it's actually 0, right? If you see an e negative 4 over here, that means it's 10 to the negative 4th. So it's 0.000 something. So you got to be careful, right? And don't write your answers with the e in it. You know, if you want to write this when you copy your table, write -1 times 10 to the negative 4th, right? A big deal on the AP test is not to use calculator syntax. Use math notation. I think you ought to just put -0.0001. And I'm not going to go around counting your zeros or anything. It's not that big a deal. But this would be like -0.001, -0.002. Don't put the e notation, okay? All right. So, and sometimes you get numbers that are in the thousands over here. Well, what's happening is that's probably going to infinity, and you can just look at your graph and see if you've got an azimuth. Does that answer that? Kind of. Is there another one you want to see there?
Like number 6, I guess.
Number 6. Okay. We got time here. We can do one more. So let's go into here, and let's put number 6 in here. So, so what do we got? We got what's on top of number 6? Sine x. What's 6? I'm sorry. What? Sine x. Okay. Minus x minus 1/6 x cubed. And on the bottom, x to the 5th. Okay. And so that one looks like so. Now, this is as x approaches 0. So I would actually just peek over here to the graph and look what's happening. It looks like it's going down to negative infinity on both sides. And that's what this table is showing right here. So when I arrow on this, so I arrow here, I look at my number, it's negative, that's in millions, right? So that's telling me negative infinity, and that's what this one is too. So the cars don't meet. I mean, they're both going to negative infinity. We'll talk about infinity more in chapter 4, so you know, it's not a big deal to me. So if you just say does not exist, or if you put negative infinity, I'd probably take you to one of those. That makes sense? So that's what you're looking at when you see that table, right? And again, we don't even care about the undefined, but the graph can help you too. The graph can help you see those as well. Okay? All right. So let's go to the book homework then. In the book homework, we have this situation here. Right? We're dealing with the chart. They give you a graph of little f, which I've kind of sketched here, and they're asking you questions about big F mostly, right? And so I've labeled my chart accordingly. And let's just run through those answers real quick. We got time to do this because this is important here. All right. So 3 says, what is the slope of f? Well, the slope of f would be little f. So at 4, aren't you just looking for the y value? And it is what, 5?
Yep.
Easy enough. Where is big F increasing? Well, big F's increasing when little f's positive. That's all the time. This graph is positive all the time. So 0 to 10. Where is big F have points of inflection? Big F will have points of inflection when you change these two columns. That is, you go from up to down or down to up on little f. So that would be at this local max and local min. 1 point something, 8 point something, whatever those are. You just estimate where those are, right? Now stop me seriously at any time here if something goes by you. Where is big F concave down? Big F's concave down when little f here is decreasing, which would be from this peak to this peak. All right? All right. What is big F double prime of 5? Well, big F double prime is just the slope of this graph. So that would be this tangent line right here. Right? Rise over run. It's about negative 1.5 or so. It's like you go over 1, down about 1.5, somewhere in that ballpark. Why does big F double prime have its minimum value at 4.67? Well, that's right in here somewhere. What is that? Inflection point. Big F double prime have its minimum value. Well, big F double prime are these slopes on little f. These some slopes are positive. Well, that won't be a minimum value. Some are negative. That'd be the min value. The one that's the most negative. Well, the one that's the most negative is right there. Okay? At the inflection point. Find an equation for the tangent line. Well, the tangent line of f at the point 0, we need the point and we need the slope. So we need big F of 0 and we need big F prime of 0. Well, what's big F of 0? They told us. 10. What's big F prime of 0? That's the same as little f of 0. So you just read off the graph. You go to 0, you read up, it's a 7, and then you got the equation of your tangent line. Y equals 7 times the quantity x minus 0 plus 10. Equation of the tangent line, right? Yes? Okay. Yeah. No one's ever asked me that. L, I guess L, it is. L of X, L is a function. I think that really more comes from geometry, where you name a line with a capital R, so you name it L, and not so much the equation. But yes, I would take it. I would take it. But I can't say I've ever seen that. So congratulations, that's a first. All right. Does L lie above the curve? What does it take for a tangent line to be above the curve?
Has to be greater than the slopes that come
Yes.
out.
Yes. No. Well, she proved me wrong on that one quiz question. So every now when Brenda speaks, I listen. Really. Before I'm going to shoot her down. Wait a minute, she's probably right. Yes, that's true. What does it take for L? What does it take for any tangent line to be above the curve? And Carly questioned me on this at lunchtime, and she's exactly right. I didn't think about this, so maybe we do need to think about it a little stronger here. Anybody? What's that mean if L is above the curve? The curve is what? All right. Here's a curve. Let's draw some tangent lines. Here's one. Yeah, okay. That's not what you do. There, geez, I'm good. All right. Here's. Yeah, they're attached. All right. Imagine. You have to have some imagination to take calculus. For me. All right. So imagine every one of these is a tangent line and only touches the curve at one point. 1, 2, 3, 4. Which one of those are above the curve? 1 and 2 are above the curve. These two are below the curve. So one more time. What's it take? What does a curve have to be, or what does attribute does a curve have to have for the tangent line to be above it? Has to be concave down. Concave down, the tangent line is above the curve. Concave up, the tangent line is below the curve. Okay? So, the question, again, does L lie above the curve at 1 is exactly the same question as asking, is big F concave down at 1? Why didn't they just say that? Well, because they want you to be able to know what's going on there. So, when is big F concave down? When big F prime is decreasing. So we have to look at 1. Is it decreasing? It looks like it's still on its way up. And so the question, the answer is no, it is not lie above the curve because big F is not concave down. Because big F prime is not decreasing. That would be kind of your explanation. All right, finally the last two. Is big F of 5, could big F of 5 equal 5? No, this is a speed limit law. Hey, I finally found a good use for the green color. That'll look good over here. All right, so here's big F. We know that at 0, it's at 10. When it goes over to, what kind of problem is this? Speed limit law. So could big F of 5 equal 5? So could it come down? No, these are the slopes. The slopes are all positive. Big F has to go up. so it could not equal 5. No way. Could it equal 15? No. We just said it's going to go up, but now the question is, how far does it go up? Could it go over 5 and go up 5? Well, if it did, the slopes would have to be about what? About 1. What are the slopes? A lot more than 1. They're like 7 and 6. So if it's going to go over 5, it's going to go up a lot more than 5. Okay, as a matter of fact, when it goes over 1, it will already have went over 7 or more. So when you go over 1, you'll be up above 15, and it's on its way up. So it couldn't equal 5 for sure, and it couldn't equal 15 either. Okay, it's a speed limit. All right, let's talk about number 21. All right, this is really an important kind of. Ooh, yeah, that's not gonna work. So 21. This is going to be on your quiz for sure. A problem like this could be worth 6, 7, 8 points. Okay, because of the various parts. Very particular about how you show your work in this. As I went around, I saw a lot of good stuff. Saw a few missing things, but saw a lot of good stuff. So they tell you that the function g of w, is it?
Yep.
Is 7w to the ninth. Minus 18w to the 7th plus 63. And they want to know when that's increasing, when that's decreasing, where its local maxes are, and where its local mins are. So we come back, think back to our chart here, and we know that, okay, if this is G, this top row is G, we want to know when it's increasing, when it's decreasing. We want to look at G prime. When G prime's positive, when G prime's negative. Now, we also remember that if we had a G prime graph, you know, that we would always look at these points right away, right? And we would care that it's negative, and then it goes positive, and then it goes negative, and then it goes positive, and then it goes negative. And if we knew that on a G prime graph, man, we know everything. Local max, local min, increasing, decreasing, stationary points, we know everything, right? So if we had a G prime graph, that'd be great. Well, unfortunately, this is no calculator, and we're not going to have a G prime graph. But we can get a G prime equation, right? So the G prime equation is 63w to the 8th, 126w to the 6th, and the 63 turns into 0. Now, if we were doing this graphically back in chapter 1, we would first care about where G prime was 0. So that means we're going to want to solve this and see where this is 0. So we have to do some algebra. So in a problem like this, we would factor out. Turns out 63 goes into both of those. And w to the 6th, leaving us with w to the 2nd minus 2. Correct? Now, why did we factor? Not so we could divide, but so that we could set each of the factors equal to 0. Right? And on this one, we can divide now by 63, which that tells us w to the 6th is 0. And then the 6th root of 0, of course, is 0. And then here we would add 2 to both sides. And what do you get when you square root? Plus or minus. Very important that you have both of those. Plus or minus square root of 2. Unless they would have said, given us a domain. If they just said, find the local maximum, you know, from 0 to 20, you know, then we would have ignored the negative one, right? But they did not give us that, so we assume it's over the whole interval. Now, it would be nice to know, it's not necessary, but it'd be nice to know this is a ninth root, or a ninth power polynomial, which means it's going to have kind of tails going opposite directions. Now, it's a ninth power. It could have as many as 8, you know, humps in there. So it could have all kinds of local maxes and mins. But it does have this kind of look to it. All right? So now, if we were doing this graphically, we would care about now in between the zeros, where it's negative, where it's positive, right? How can we do that with this? Do the G prime number line. Now, some of you that I was helping, I noticed did not have it labeled. Make sure you label that G prime, because we will get into some problems where we do inflection points and concavity, and then we'll be using G double prime. So you'll have two number lines in one problem. So you have to make sure you label them. All right? Now, if we were doing this problem on the quiz, you'd probably get 1 point for having your derivative. So you need to have that on your paper. Maybe even a point for setting it equal to 0. Another point for solving it correctly and getting these stationary points. Okay? Another point for a proper number line. Even on the EP test, they ignore your number lines. They want to see your explanation. But I want you to get used to doing it, so I'd probably give you a point for having a proper number line. I want you to get in the habit of doing that. All right, and now we're going to pick some numbers in between. So we better know what square root of 2 is, roughly. About 1.4. So a number like 2 would be good over here. 1 would be good in between. -1 would be good here. -2 would be good here. Don't put hash marks with those. Only put the hash marks on your stationary points. Okay? So now we're going to look in between. Now where are we going to plug those in? G prime, because we want to know when G prime is negative and positive. So we have to plug in G prime, and that's important because we will be doing some other problems like this, but we will be plugging into the G, the original function. And so we really got to keep track of what it is we're trying to find here. We want to plug into G prime. I would suggest plugging into this version right here. Okay? So I take a -2 and I plug it in to the 6th power. Now I don't care what that is other than the fact it's positive. Matter of fact, w to the 6 is always positive. Doesn't matter what I plug into. So I'm not even going to plug into that anymore at all. I just know that's always positive. Okay? So -2 over here squared is 4. 4 minus 2 is positive. Positive times positive is positive. Put -1, of course that's always positive. -1 squared is 1. 1 minus 2 is negative. Put in a 1. That's positive. 1 minus 2 is negative. And then finally put in a 2. That's positive. Put in a 2. 4 minus 2 is positive. So my number line looks like that. So let's answer the question. A, where is G increasing? -infinity to -√2 and √2 to infinity. Where is G decreasing? -√2 to √2. And we don't include those endpoints ever when we're doing the chart stuff. Now this is the one, for you guys who were gone yesterday, this is very, very important. C says, where is there a local max? Well, back here when we were doing our graphs, it would have been whenever it changed from positive to negative. Well, same thing here. So it would be at x equals -√2, but that's not enough. You've got to write out a justification. G prime goes or changes positive to negative. I usually will not write this all out. I did it yesterday. I'm doing it again this time. Most time I won't, but you guys need to. G goes increasing to decreasing. So anytime we're switching columns in the chart, which happens for local max mins and it happens for inflection points, we need to write that out. And then D, the local minimum, is at √2. And sometimes you have more than one local max. One justification is good. If we had 3 different local maxes, you could have listed all 3 there and have one justification because it's the same justification for all of them. All right? And then you would have needed, again, your justification for your minimum. Except it would have been negative to positive and decreasing to increasing. Okay? I did see some papers that look very good. But think about all the points there. One for doing the derivative, set it equal to 0, solve it properly, do a number line, and then getting each of these parts correct. Okay? So if you do a good job on it, that can be real helpful. All right. So we want to be able to do that chart stuff. So what we want to do next is I've got a couple of things that we skipped over in section 3 and in section 4 that I want to get to, and then we'll pretty much have everything. We'll do some review on Monday, and throw out some things and do some long way practice and some of that, and then be ready for the quiz. Yeah.
Just as a general rule of thumb for factoring, is it bad to divide by a coefficient if you set it equal to 0?
It is not bad to divide by a number. It's only bad to divide by the letter. So right here, I could have divided everything by 63 and gotten that out of it. That would have been fine. Coefficients are fine to divide by. All right. So you might want to get some notes out here, and there's a couple of things we want to put down and talk about, and then we'll get to work on some homework. All right, this first thing, if you want to follow along, not necessary, I think is on page 106, but we'll write it up here on the board, what you want to write down. And I'm gonna write it a little differently than page 106 does, but okay. We're going to talk here about what it means for a function to be continuous. Now, so far informally, we've talked about that. Continuous function means you don't lift your pencil, there's no breaks or gaps. It's just good things happen when a function's continuous. All right? But now we have enough information to talk about it more formally. So here's what we're going to write. A function f is continuous at x equals a if there's going to be three things. And we need to basically memorize these three things. Okay? First of all, f of a is defined. Now in your book, they look at it from the negative viewpoint. They say a function is discontinuous if f of a is not defined. Okay, so we're going to talk about what it takes for something to be discontinuous. Okay, now what could make that fall apart? What could violate that scenario? Well, a hole in the graph, right? At point A. Function's not defined. So that function would not be continuous. We talked about you shouldn't have to lift your pencil, right? So you got a hole in the graph, you have to lift your pencil, that kind of thing. I mean, again, that's kind of an informal definition, but that is discontinuous. Another thing that would cause that or violate that would be a vertical asymptote. Okay, those would be the two main things that would violate that right there. And so again, those would be examples of functions that are not continuous. Okay? The second thing that has to happen, and this is what we had to wait for, is we now know about limits, and so this is the next piece. The limit of the function as x approaches a must exist. Now notice the wording there. Functions are defined or undefined. Limits exist or do not exist. Okay, so we want to use the proper terminology there. We don't want to say a limit is undefined. Okay. Now, what would violate that? Well, a simple one where the limit doesn't exist, we've seen, is a break in the graph. Right? See, that doesn't violate number one. The function's defined everywhere. The function has an output everywhere. Okay? So that doesn't violate number one. But the limit would not exist. And clearly that's not continuous. Right? A function is not continuous if it's got a break in the graph. And then a vertical asymptote again would violate this. Right? The limit, this is like the one we were talking about before. From our worksheet. The limit doesn't exist there either. The cars don't meet. So the limit would not exist. And then the third one that has to happen is the limit as x approaches a of f of x has to equal f of a. So there has to be an output at a. The cars have to meet at a, and the output and where the cars meet has to be the same. What would be the one that would violate that? Yeah, this one we've been talking about, right? This would violate that situation. The limit would exist, so number 2 would be okay. The cars meet. Number 1 would be okay because there is an output, but they're not equal. And that, again, is clearly not continuous. We'd have to lift our pencil at that point. That's not continuous. So when you see in a problem, assume f is a continuous function. That's a good thing. You're like, yay. It's smooth. Smooth is probably not the right word. Because a V-graph. Would a V-graph be continuous? cars meet? Output the same as where they meet. V-graph would be continuous. Okay, so I shouldn't say smooth. But if it's continuous, it means there are just no gaps or breaks or jumps or holes or asymptotes, that kind of stuff. Okay, now let's talk about that V-graph thing a minute. That's a special case. So let's write down one more definition. A differentiable, see if I can spell this right. I think that's right. A differentiable function is continuous and f prime of x is defined, now, exists, that's weird, we usually talk about the derivative exists or doesn't exist. That one we could probably use either one. Everywhere. It's a little bit like the rectangle and the square. Okay? So, if you've got something with 4 right angles, 4-sided figure with 4 right angles, okay, it's a rectangle. If you add one more condition to it, that it has 4 equal sides, now you got a square. Well, that's what happens here. You got a continuous function that has to have those 3 pieces. Like a V-graph would fit that. But then if you add one more piece of information is that it has to also have the derivative exist everywhere. Would the V-graph fit that? No. And so there'd be 2 main things that would violate that. This and then this, your vertical tangent. Right? So those 2 would be continuous functions, but would not be differentiable. Just like you can have a rectangle, it's a rectangle, but it's not a square if it doesn't have the 4 right sides. Okay, so would all differentiable functions be continuous? Yes. The differentiable is like the square. All squares are rectangles. A differentiable function is continuous. And it has this extra piece of information that means the derivative is. So when we talk about smooth, we're really talking about differentiable. Because not only is it connected everywhere, no breaks or gaps, not only is it connected, but there's no sharp points either. So it's smooth. Okay, so when you see that a function's differentiable, that's really, really nice. Okay? Because then you know you don't have these sharp points and that kind of stuff. All right, so that's continuous and differentiable in a little more formal setting. All right. Next quick thing, and then we'll get into talking about some homework stuff. Let's say we had the function f of x. I'm going to put that right in the middle because below it, I'm going to have f prime of x, and above it, I'm going to put big F of x. Let's see what we can do with this. So I'm going to make little f be x cubed minus 2 x to the 1/3 plus 5. So f prime would be the derivative of that. Let's write that down. What would be f prime? 3x squared minus 2/3 to the negative 2/3. That's it, right? Plus 0. All right. So on the quiz, there might be a few where you just simple kind of power rule, maybe a fraction or so in there, whatever. All right. Now, yesterday we learned about big F, which we call what? Antiderivative. What would be the antiderivative of F? Do we have a guess on x to the 3rd? I would agree that it's going to have an x to the 4th in it. One of the things you're going to find about antiderivatives, we're not going to get into it very heavily right now, but when we get into more, they're more of a guess and check kind of thing. Derivatives have a rule. But antiderivatives are more a guess and check. How do you check if you got the right antiderivative?
Then you
Do the derivative, right? So you would say, well, I know the power's going to go up. We know, I mean, that makes sense. So do the derivative and see. Well, you would have a 4 down in front, x to the third. Oh, we don't have a 4. So how about we stick a 1/4 on there to take care of that? And that's exactly what you do. Now, you could say, though, that we could invent a rule for this. I mean, think about it. When we did the derivative here, it was a two-step process. We brought the power down in front and multiplied. So we multiplied by the power. And then our second step was subtract 1 from the power, right? So if we're going to reverse that process, wouldn't we do them backwards and do the opposite? So instead of subtract 1 from the power, we would add 1 to the power. That would be our first step, not our second step. We're going to go in reverse. So we'd add 1 to the power, and then instead of multiply, we would divide by the power. Sure enough, so we'd add 1 to the power and then divide by the power. Now, having that little rule, and actually it's written this way, it's written as x to the n plus 1. I think it's in your book in that section. And then divide by n plus 1. Now, for a lot of antiderivatives, we don't even have a rule. It's just kind of you got to think in reverse. But for power rule, we kind of do. It's raise the power up 1 and then divide by that new power. That's your antiderivative. That really helps on ones like this with fractions, because what you would do here is you would just leave the 2 there. The x, the new power, would be what? 4/3. We would add 1 to the power. And then we're supposed to divide by the new power. Well, if you divide by 4/3, that's times by 3/4. And so we won't ever write divide by 4/3. There's no sense to. You might as well just right away flip it and multiply by 3/4. And then we could go ahead and put those together. So that would be 6/4 or 3/2 x to the 4/3. So far I got 1/4 x to the 4th minus 3/2 x to the 4/3, I think. And again, we could check it. So let's do it. So let's bring the 4/3 down. 4/3 times 3/2, that'd be 12/6, which is 2. And we would drop the power by 1, which is that. Yeah, check. So there's going to be some in your homework where they're going to do that. They're going to give you an antiderivative and say, check that this is the antiderivative. We'll just do the derivative. See if it is. All right, then we got the 5. What about the antiderivative of 5? 5x. That is correct, because think about what you would do in reverse. Remember, there's like an invisible x to the 0 here. Right? And so you could raise the power up 1 and divide by the 1. The simpler way to do it is just remember, whenever we do 5x, that's like a line, has a slope, it's 5. So whenever you have 5x, do the derivative, you just throw that off the x, it's 5. Same thing with antiderivative. You're doing the antiderivative of a number, you just stick an x on it, and you got it. Anything else? Remember when we talked about, here's a G prime graph, da-da-da-da-da, and then you were supposed to draw the G graph? Were we really doing the antiderivative then? Remember that? Here's a G prime graph, you draw G. And then we would say, where does it start? We say we don't know, wherever. Because there can be an infinite number of them, they just be vertical shifts. So some wise guy in the other class said, when we got done, because I'll be honest, I was just going to stop, because this would be fine for what we're doing. Somebody in our class says, couldn't you just tack on like a +2? Isn't that true? Sure. To do the derivative, what happens at 2? It goes away. But isn't that your vertical shift? Right? Isn't the +2 just the vertical shift? And actually, I'm glad they said that, because there is one of your homework problems, I think, that it says, find 3 antiderivatives. +2, +3, and +4. Exactly. But yeah, put a +2, put a +3, put a +4. Now, to be honest, what we normally do, if it says find 3 antiderivatives, or if it says find a specific antiderivative, then you can just leave it off too, because then it'd be like a +0, right? So you can always just leave it off. But, or you could put a number there. there's also some, and this is not a big deal for now, but what we'll do later is we'll just throw on a C for a constant, plus C, which just reminds us that there are an infinite number, it is just some vertical shift, and C can be positive or negative, right? And so we'll do something like that. But for right now, don't worry about that. Okay, but yeah, when you see the homework where it says find 3 antiderivatives, that's what they're talking about. Okay? Because as soon as you do the derivative to check, the constant goes away anyway, and so you don't have to worry about it. All right, that is it for new stuff. Let's just get out your worksheet, because the back side of the worksheet is going to be part of our homework today. And it's not really new because we did this in our homework the other day. It was number 34 and 35. Remember that one that had the delta x in it? The delta x. This is the same exact thing. All right. So I just want to begin our homework by wrapping back around now to the very first thing we did here in chapter 2, which was this special, this thing right here, which was this special limit of slope. Okay, so you just got done doing a worksheet on the back side with the tables. There were just a bunch of limit problems, and you want to see where the car's meeting and what's the limit answer. That's all it meant to you. This page are going to be special limits. They're going to look like this. They're going to look like f of a plus h minus f of a. And if you remember what we did when we did 34 and 35, we said the key is look at the a plus h. The a plus h gets plugged in where the x must have been in the function. The a plus h is plugged in where, remember peanut? And we put peanut in, right? That's the a plus h. That gets plugged in. So in this worksheet, let's do this first one together. So it says, you're supposed to identify f of x and a, and then use your calculator to estimate this value. Now I want you to do the tables, but you don't, if your calculator still works, but you don't have to write the table on this one. You don't have to write the table. But I would like you to use the table just to get used to that again. So here's what you'll do. So you'll say, all right, this piece right here represents what function of x? 2 to the x power. Now, why does it represent that? Because here's the a plus h right there. The 3 plus h, that is the a plus h. That got plugged in where the x was. So that has to be the x, 2 to the x. All right? And what a are we doing? What derivative are we doing? What's our a value? That's got to be the 3. If this is the a plus h, then the 3 has to be the a. Now, it's important for us to understand this. So let's go ahead and do this on our calculator. Let's go ahead and put in. Now, when we put in our calculator, though, can we use h? No, we have to use x, right? We have to use x. But what you're about to do right now is the same thing you did on yesterday's worksheet. You're going to plug this thing that I've got circled in red in for your y equals or your f1 equals. Okay, it's taking me forever, so I'll let you guys do it. Okay, what do you get? Or do you get 5 point something? If I remember from last period, it was 5.545, I think. The 3 decimal places. Now put your arrow so the cursor has a highlight so you get the little yellow sticky so you make sure it isn't like a 10 to the negative 4th or something like that. But I think that's what it's approaching. Now remember, your table start is still 0. This is still the limit as h approaches 0, right? Not 3. Don't mix up that 3 in here. 3 is the a. 3 is in here. All right. It's still, why is it still h approaches 0? Because the 2 points are getting really close together. This is the derivative. Remember what this, see, so what's happening now on this side of the worksheet? The other side of the worksheet, we were just doing the limit, where do the cars meet, look at the table, put that number down. Now, we're doing the same thing, but this number now has added meaning. It not only means where the cars are meeting on this function here, but it means what else? This number means what else? It means the slope of what function?
The x function.
The 2 to the x function at 3. You see what I mean? This is a special limit. So we do the limit like we did yesterday. We look at the table. The cars are meeting at 5.545. As x approaches 0, we used x instead of h. But because it has this special look to it, this 5.545 also means the slope of this function at 3. Right? Okay. I mean, it's important for you to get that this is a number. It can mean a lot of different things. In this case, it means 2 different things. It's like, let's say the 15th, right? I mean, that could represent today's date. It could represent, I don't know, how much money I have on me on a good day. My ACT score. I mean,
In the 4th grade.
it could, unfortunately, a little. Anyway, right? So, right? I mean, so this 5.545 represents 2 different things here. I would want you to understand it. All right. Now, just for the heck of it, and I'm sure you didn't even think of this at the time, but turn back to the other, flip over to the other side of your worksheet. We were working these limit problems. Now these have x's instead of h's. Do any of these have that special look to them? Were any of these actually derivatives kind of in disguise?
Yeah.
That one?
Yeah.
If we flip that around and made it 1 plus h, right? Minus and then square root of 1. How about this one?
Yep.
Right? This one also is. This one is. Okay, now 4 isn't. I think 5 really is in disguise. This is actually like number 34, number 35, one of those. This is like 0 plus x. And then cosine 0 would have been here, right? Now those aren't. Now I'm not going to give you one of these and say, is it or isn't it, you know, that kind of thing. But, yeah. So some of them on this side actually were that as well. All right. So you do not have to copy down the table. So all you need to do is write down what I just had written down. F of x equals 2 to the x. F prime of 3 equals. Write down the answer that you get from your table. And that's good. That's all you need. Okay? All right. So go ahead and work on that. And then I will put, I've got some other ones from the book here. Let me put these up here. Okay? Here's a few problems from the book then to add to that. Okay? This, one last thing, then I'll leave you alone. This is the 2-3 stuff here is from, is about that continuous function stuff, those 3 things, right? So you'll be referring to that. In this section, you'll be referring to, you know, limit exists, f of a is defined, you know, that kind of thing. And then these problems down here will be those kind of those antiderivative. Here's number 20 is another practice on local max, local min, the number line, doing an f prime number line, that kind of stuff. Okay, so those are kind of some practice on some of the new stuff we did today. All right, rest of the time's yours to work. Does he still use his calculator?
I think so.
Um, Just text him back and say probably. Just tell him I said probably. You'll figure it out. And when, or no, say probably, and then say that I said, and when he figures it out, then let me know. Okay. I mean, I will. I'll play around with it and see. But
It is one, but square root of fx is 1.
A, see, we have to look at two different things, because the first thing you want is what is the.
can I go use this? Yeah.
So you use the message instead of so here, this two different function. A is what?
Hey, tell him to
And here, you're adding each.
on the calculator number.
So.
In the menu, number 7 is matrix and vector, and there's all kinds of different matrix options there.
Here, this is.
So,
With A.
yeah, it looks like it'll do all kinds of stuff with them.
So what
It's just under the menu. I can't believe we wouldn't have found that.
out A, which here is square root of x, and then what A and what x is. Yeah. Just because they have so many things.
Two times the six, three. Minus two times the sine three. Oh, we didn't do that. Figured that, yeah, it'd be 0, 0. So you have to keep going. No, it was great. No, I was gonna say, I was pretty sure. Oops. That's not right.